Yeah, so hello everyone. My next talk is on particle disaggregated cache for Apache DataFusion. And yeah, let's get started. I'm Xiangpeng Hao from University of Madison. I'm first year PhD. So unlike other speakers who already have a lot of experience in the industry, I'm still a student here. And my studies focus on database and storage systems. And I have been building high performance and super low level systems for quite a few years. And I started like writing Rust like in 2019, like 5 years ago. Yeah, so it's when Rust is still very young. Okay, so today my talk is about the disaggregated cache. So I have a very high level picture here. In a modern data lake architecture, we have object store, we have compute node, and we want a cache in the middle. And that cache, yeah, we will dig into this later, but in a very high level, we have a question of should this cache node have some computation power? By having computation power, I mean, should we push down some of the predicates to the cache node? And if we do it, we can sometimes easily overwhelm the cache node. And if we don't do it, we have very high network traffic here, which is bad. And so that is the key question we're going to answer in this talk. And we have like a architecture like this. Okay, so the system we're building is we are building a disaggregated cache in the middle of object store, and it's a compute node which we evaluate some of the queries on the different parts of the system. So we call it like a split SQL, push down, down right. And yeah, so we have some tricks to make sure the caching is cost effective and is also very fast to run, which we'll show next slide. The high level result is basically if you cache anything, you have to make a trade-off between query performance. For example, if you cache Parquet, you're going to have some high query latency here, but the cost is pretty low because Parquet is pretty complex. But if you cache Arrow, you get a low query latency, but your cost is very high because Arrow is memory hungry. And what we are achieving here is the best of both worlds, which will discuss how exactly that works. But that is very high level of what we have achieved. Okay, this is a query. We'll dig into this later this talk. Okay, so the outline is we're going to discuss why disaggregated cache is the future. And the second part is having that disaggregated cache. We have to answer the question of what should we do in that cache node, right? And the third part is how our system deal with the problems we have seen before in like disaggregated cache. And the part 4 is the evaluation of how good we are. Okay. Okay, yeah. So modern data lake architecture look like this. Okay, we have an object store on the left, so everything dump into object store, so we don't have to manage the disk of our own. And we have we have compute node on the right-hand side, which like whenever we have we need more computation power, we just spin up more compute node, which they all connect to the same object store. So if there are some queries goes to a compute node, we just download the file from object store and run the query on that file, and we return the result, drop the file potentially, because the compute node is stateless or serverless. We want. So if we have more queries, we just spin up more compute node, and they will handle different user requests. And this is called diskless. This is called serverless. And we want this clean separation of a disk and like disk and computer storage, so that we can scale independently and we can lower our management cost. And that is user query on the right-hand side. So in this modern architecture, object store is our new disk, and EC2 or Lambda or whatever virtual machine is our new new CPU. So like the conventional system, we have CPU, or we have like memory or cache in between the CPU register and the disk to bridge their performance gap. the question in this modern cloud native architecture is, what is our cache? So what should our cache look like? So there are several options. The first obvious option is we can have a private cache. The private cache essentially says, since those are virtual machines and virtual machines has CPU, has memory, and has all the resources we want, so we just provision use the spare resources on that compute node to build a cache component. So it's very simple. The problem is also pretty obvious because we have multiple compute nodes. They serve very similar queries, so we very likely to have duplicate copies. And we cannot scale independently because if we want to have a larger cache, for example, in this node is super busy, we have larger cache. The only way we can scale a larger cache is to provision a bigger compute node, which we probably don't necessarily need it. And lastly, it has low resource utilizations. For example, on those compute nodes, they may serve very different user queries. Some nodes are super hot, some are pretty cold. So if this node is super hot and need more resources, well, you cannot borrow the resource from a neighboring node, which leads low resource utilizations. But like this architecture is very simple. It's very high performance because everything happens in the same node. Like InfluxData and Databricks are all use this approach.
Right, basically.
Yeah, yes, basically, how do you describe it? Also this approach, yeah. And option 2 is distributed cache. So the idea is instead of having each node have a private copy of the data, we build a distributed file system to connect all the resources together so that they form a unified view of the of a caching component. And this is basically have a very complex design. As you can see, each node need to coordinate with each other. You have to run consensus algorithm, which nobody likes it. And and also because the data is in fact in different nodes, you have to be careful about locality and all the network traffic, etc. But the good thing is you only have a single copy of data, so you save some resources. And you still cannot scale independently because you're still building the caching component on the spare resources of your compute node, right? And it has high resource utilizations because everything is in the same pool. If one node is particularly hot, you can easily borrow data from a neighboring node. And that is how Snowflake does this, and also Alexio. Alexio is a startup just providing this solution, which shows how difficult it is to build. Right? And the third option, which is disaggregated cache. And the idea is pretty simple. You have a cache server, which is no different from your compute server, but it's dedicated for caching, sitting between the object store and compute node. So this is closer to compute node, and the latency between those are like 10 or 5 milliseconds. This is 100 milliseconds. So cache is closer to the compute node. And you have a disaggregated cache. And the advantage is a very clean architecture. It's not super simple to build, but it's simpler than a consensus distributed system. And it maintains a single copy, so you don't have to duplicate or files on different compute nodes. And you can scale independently. If you want a larger cache, you just provision a larger node, and your compute node will stay the same. And it has high resource utilizations because everything in the same pool. And yeah, despite all of those advantages, this architecture is not super popular. And why is that? So that goes to our second part, which is to push down, not push down. So the problem here is disaggregated cache will cause high network traffic. Why is that? Because you have a caching component sitting between this, and they are all connected over network. And it's very likely that when a compute node DataFusion instance will scan a Parquet file, even DataFusion has very advanced Parquet pruning technique, you likely still have to scan a lot of data. So that means you have to send a lot of data over the network, and eventually your system is bottlenecked by the network, which is not great. And the idea of predicate push down is basically says based on this observation. So if you look at the architecture here, Apache store, cache, and compute, we often start with a memory or file system read on the cache node, and then we immediately send the larger file over the network to the compute node. Okay, that's what naive approach does. And after that, we will have some aggregations, predicates, sorting, and drawing, etc. All these intensive operators to operate on the data we receive from network and get the final result. And so we can see basically we have these two steps. First step, we read a lot of data, send over network, and then immediately after we receive the data on the compute node, we will drop most of data because most of the queries have filters. For example, if we have robotic systems, we probably only care about a particular time range. If we have a weather, weather information, we probably only care about last 10 days or something, right? So we always have most of the time we always have a filter there which filters most of the data, irrelevant data. And the idea is because caching server in this architecture, disaggregated cache, no, the caching server is no different to a compute server. It's just a virtual machine there, right? So you have some CPU power there. So the idea is we have a memory of our system read, and then we immediately evaluate those lightweight, cheap filters on the cache node. And then after the cardinality shrinks down, we'll send those data, hopefully their cardinality is shrinked by a lot, then send over network. And the compute node will continue working on the computation intensive operators like sorting, predicates, and drawing, etc. So basically, the idea of predicate pushdown is we split the query pipeline into two parts. One is lightweight filters, which cut the cardinality down, and the second part is compute intensive operators, which is more suitable for the compute node. So this is predicate pushdown to cache, and people love predicate pushdown. Here's some evidence. So before we have cloud, the system like IBM NetSA, which essentially utilize the smart SSD or smart NIC or FPGA on top of the storage device, so that while the storage device is scanning the data, it will apply the filters, utilizing the smart chip on those systems. So example system like IBM NetSA, and after we move to cloud, we almost immediately want predicate pushdown because in this storage compute disaggregated system, we very much rely on the network to transfer data. So AWS S3 Select basically says you can push down some of your queries to the object store so that the data comes out of the object store will be already filtered, so that the network cost is cut down and you pay less to the AWS. And our system conceptually is not too different. Okay, so we are essentially says in this disaggregated cache system, we want to push down the predicates to the caching server. So yeah, so this is conceptually simple. So why people haven't done this? In fact, the predicate pushdown is so popular, yet previous attempts of building those systems have failed. For example, IBM NetSA was dead in 2019, and the AWS S3 Select was dead earlier this year. And it seems something is wrong with predicate pushdown. And how do we not to repeat their mistakes? So the challenge here, or the reason we believe that those predicate pushdown system failed, is because the caching server can easily be on fire. So by being on fire, I mean we have multiple compute nodes. They will connect to the same cache node, and they will all send their cheap lightweight filters down to the caching node. And we have been done a lot of research on how should we use some cost-based approach to only push down those lightweight predicates to the cache servers. For example, we want to push down the as selective predicates as possible and as lightweight as possible, right? So that the cache server not be overwhelmed. But the problem is the caching server receive a lot of predicates, and those are already simple and profitable. But the caching server still experience is still being overwhelmed because it found that even simple filters can be very expensive to evaluate. And why is that? That goes to our third part talk, which will discuss why that happens and how do we fix it. Okay, so in our system, we have our quick store, we have a cache component in the middle, and we have a multiple compute nodes. And if we want to scale multiple compute nodes, we will all these nodes will attach the same cache server. So for example, if one of the compute nodes need to reboot or need to whatever crashed, you just spin up a new compute node, connect to the same cache node, then you don't have to warm up your cache. You can expect a stable latency, etc. So that's great. And if you want to scale a larger cache, what we do is you can easily provision a larger virtual machine there, right? Like for example, if your cache use memory to store data, you can easily provision a larger EC2 machine. In fact, like 16 core vCPU of EC2 machine, you can choose memory from like 32 gigabyte all the way up to 256 gigabytes of memory. And if you use storage to cache your data, you can easily, even more easily to attach a larger elastic storage to the caching server. And that is how high-level architecture, and we'll dig into that, how we split of a SQL. Here's an example. Let's say we have a SQL like this, select distinct URL from basically the table where URL contains the string Google. So this is a real adapted from a real ClickBench query. Essentially, yeah, we split it into two parts. The first part is the caching component, which we say we want to select all the URL that contains Google. And then we have the other part of the query, which says, I want to count the distinct URL. And that is how split SQL works. So we split those SQL into parts, and then we send the SQL to the corresponding server so that each server is specialized in evaluate those, answering those questions. So the caching specific SQL will send to the caching server, which will evaluate against the cache data. Then it will send the filter data to the compute node. And the compute node will evaluate the expensive aggregation here, distinct URL, and get the results. And that is how it works in high level. So the question here is, once we split the SQL, we have to all of the previous fancy research on how should we split it in a cost-effective way. The question remains still is how do we not prevent overwhelm of my CPU on the cache server? And the observation is even simple filters can be very expensive to evaluate. For example, let's look at this query on the top left, where we have basically we evaluate this innocent locking filters, where basically says if your contains Google. And here's a flame graph. What it looks like. Okay, so basically it's pretty mouthful, but it boils down to three components. The middle component is decompressed Parquet. So Parquet is a compressed format. So every time you have to read it, you have to decompress it. For example, you have if you have Z4 or Snappy, here with Snappy, you have to decompress the Snappy encoded data into uncompressed Parquet. And then the left part is you have to convert Parquet into arrow. So yeah, we have to operate on arrow. So that's the transcoding overhead. And then we have the time on the right-hand side, which is evaluate filters. That is actually the real work that we do to evaluate that filter. So if you look at this, the decoding over Parquet is like spending 80%, almost 80% of the overhead, and the useful work is only 20% on time. And that is why, although we have tried so hard to only push down simple filters, actually the useful work is only 20%. And that is a constant cost involved, like when we have to work with Parquet. And that is the elephant in the room. And so that's how we should optimize our system, right? So predicate pushdown doesn't like Parquet, but everyone else love Parquet. Okay, Parquet is the industry standard. It has rich features. It has great ecosystems. So you have basically a rich like a set of encodings that is basically suitable for every workload we have, right? And it's a better test. It never lost the data, and it compressed well, so that when you file on S3, it's not going to charge a lot of money. And it's actually the de facto file format for the big data. So everyone by default use Parquet unless you have a specific reason like us. And we also use Parquet. Yeah, we don't change Parquet. Spoiler alert. Okay, decoding Parquet is CPU intensive because you have to do all those 3 steps. You have to decompress it. Parquet is compressed using general purpose compression algorithms. And you have to decode the metadata, which is somebody complains is slow. And then you have to decode your entire results of the data. And this is not a problem in general for most of the compute servers, because most of the time you read Parquet and do a lot of things, and decoding Parquet is only a tiny part of your total time, which we will show later. So it's not a problem for the compute server, but it is a problem for the caching server, because remember that our caching server have relatively weak CPU, and it is shared among multiple compute nodes. So the problem with decoding Parquet is almost only a problem when we have to do predicate pushdown on the cache server. So it seems that faster decoding is all we need. Then the most obvious question is we just switch to a different file format, right? So like for example, a system like Nimble from Meta, DuckDeep use their own file format. Vortex is building a compressed arrow for their own format, and the Landscape also build some different file formats. So people are building different formats, but in my opinion, this is small win, big loss, because we lost all the other nice Parquet features, and Parquet is the industry standard, means like a lot of system knows to operate on that system, operate on that file format. And if you change Parquet, if you change it to a specialized format, you kind of like a vendor lock into a particular company, right? And it's also slow adoption. For example, Parquet itself is evolving, right? It has been adding new data format, data format and new encodings. But for example, like Parquet data page v2 was released almost 10 years ago. Yet, most of the Parquet files still using the Parquet v1. So evolving Parquet or having a Parquet v3 is also not a solution for us. And it can take more than 10 years to actually adopt a new, better Parquet format, which is longer than a PhD. Yeah, so we're not doing that. So the question is, if we don't change to a Parquet file format or Parquet format, how can we do better, right? The second option is, since decoding is so expensive, the natural question is, why don't we just cache the decoded value, right? So what if we just cache arrow in our caching server, then problem seems to solved. We actually implement this and run a benchmark, see how it works. So basically, this is ClickBench, and it has 43 queries. ClickBench is basically a standard, like I think it's a standardized query benchmark, basically exercising a lot of the real query semantics. And those are 43 queries, and the y-axis execution time, so the lower the better. And we basically implement two variants. The first variant is caching parquet, which everybody does. And the second way is caching arrow. So caching arrow basically says we can skip the decoding phase, right? And so we can see most of the queries, actually all of the queries has better performance by caching arrow. And some queries, like those queries, have like small performance gains because decoding packet, this is actually the cost of decoding packet, right? But because decoding packet is only a very small part of the entire query time. And that's why most people are fine with packet. And for some other queries, like those 2021, those are like future dominant queries. Basically, those queries says, okay, I'm going to select all the URLs where URLs match some patterns. So for those future dominant queries, we see like 4x improvements because those queries are really spent a lot of like the decoding packet, the constant overhead of decoding packet is dominating the total query time. But for other queries, actually a lot of other queries, those we only have small improvements on compute intensive queries. So it seems fine, right? So like the caching arrow always get better performance. So why don't we do it? Because arrow is not as compressed as Parquet, and it's actually very memory hungry. So we want to know what are the costs. This is basically the same experiment, except that the y-axis is now the memory usage. And this time, still the lower the better. So caching at Parquet, we consistently get very low memory, memory usage, indicating that we only need to provision smaller nodes to run those queries. And for the caching arrow, we actually see there's an auto memory arrow there. So arrow is really memory intensive and memory hungry. And we have seen that we see like consistently almost like 5x higher memory costs across the board when we want to cache arrow, we want to get rid of that decoding overhead. Yeah, question.
So for the arrow, did you like try tuning the arrow at all? Because like one thing I found when like at some points we were like comparing arrow to Parquet is like Parquet by default dictionary encodes every column. And arrow generally, unless you select specifically a dictionary type, which like are supported, but you know, not that supported, not that common, you don't get that. And like what we found was that, oh, actually a lot of the compression we're getting from Parquet isn't even from like the ZSTD compression. A lot of it was just from dictionary encoding. You can actually do that in arrow and memory or on disk or whatever.
For this part, we haven't like tuned the arrow input representation, but I think yeah, it's a great direction. Actually, we explored a little bit the data set.
This particular data set is like your observability data set, Influx's data set has a lot of repeated strings, so it does actually compress very well dictionary coded data. The ClickBench data set is not the same, like it doesn't have lots of repeated exact strings.
Yeah, but like we actually we will go to how we tune the arrow a little bit to get it. Okay, so the second option, which we cache decoded values, we get performance improvements varies, but the cost is always like say 4x higher. So we were not doing that. Then that goes to our what we actually need. So what we actually need is a cache-specific file format. It is file format that only happens in the cache. What happens in cache stays in cache. So no other system, no other components knows what we actually cache. Okay, because we have the freedom to transform the cached data whatever we want. As Andrew just mentioned, we can tune the arrow, we can compress the arrow a little bit, etc. We can do all of those new opportunities there to make the cache specific file format efficient. So I'm trying to give an idea of why there's hope in cache specific format, why we can do better than Parquet in this case. Okay, so the first line of direction is we're going to leverage some modern encoding algorithms. So Parquet has been like invented for 15 years ago, and at that time we don't have those fancy encodings people invented recently, like FST or FastLane, etc. So those algorithms tend to have SIMD friendly. So SIMD basics has some CPUs have super wide registers that you can process your data in single instructions. So that is super efficient. And we can also have fine-grained decodings. Like Parquet has the problem of every time you want to read a particular element in a page, you have to decode the entire page, which can be quite wasteful. So in our system, we want to be mindful about if we want to decode some data, we only decode the relevant data. And the third part is we also want to evaluate predicates on encoded data, right? So Parquet was designed not really with this in mind, but in our new system, we can figure out how to evaluate the predicates on directly on encoded data so that we don't have to decode the data beforehand. And the second part is modern trade-offs. So Parquet was like 15 years ago. At that time, SSD was still not a big thing there. And now we have super fast SSD. We have we want to make different trade-off of I/O time versus decode time. So ideally, we want the I/O time roughly match with decode time, so that we can do we can interleave those two tasks. Right? And also in modern platform, like 15 years ago, we store everything on premise on our same single node, and now we store everything in cloud, right? So we have different compression ratio versus access cost. For example, in S3, downloading 1 kilobyte of S3 is cost the same as downloading 1 terabyte of S3. So that is modern trade-off. We want to be mindful about the platform, about the devices, modern hardware, and that's why there's hope. And yeah, we are going to design our cache-specific format just for the caching node, but also because like having a new file format is really challenging. We're not going to cover every data type here. And what I'm going to show is how we encode string, okay, and other data type are in principle they are similar, okay. So here's the challenge. We have a string of arrays like Apache Arrow, Apache Parquet, they are variable lengths, Wisconsin-Madison. And the question is, how can we encode this array of strings better than Parquet? So what Parquet does is it run a dictionary encoding and run the general purpose compression algorithm, which doesn't do well for the like fine-grained decoding, etc. Right? So what we do here is, first of all, we identify some of the strings are like repeats a lot of times. So the first step, we just do a dictionary encoding, which gives us 5 unique values: Apache Arrow, Parquet DataFusion, Madison, Meetup, Madison. And then we have an array of codes, which basically 0 means it points to Apache Arrow, 1 is Parquet, and 4 is Jupyter Madison. Then the next step is we found, okay, we only have 5 unique values. Why do we need to use like 32 bits to represent the codes, right? So we run a FastLane encoding. Basically, it's an integer bit packing algorithm which can do massive amount of SIMD instructions. So we run a FastLane there and compress those unsigned integers into just 3 bits, because 3 bits is enough to represent 5 values. And then how can we do even better, right? We observed that there are like repeating substrings. Apache appears 3 times, and Madison appears 2 times. Then we can break those long strings into smaller strings, and we can run FSST, essentially FSST algorithm, which do the job for us. So it has symbol table. which says Apache is A, arrow is B. So here Apache arrow is AB, and the Apache Parquet is AC, etc. Right. So having those this compression, and this is shared among multiple arrays. So the cost of this simple table is like a negligible. So we boils down to those very short string short arrays, and that gives us to a size of 14 bytes. That is like for this workload, this is almost 10x compression, which is great. And how does this satisfy our requirements? Yeah, this is integer encoding. We also handled there. We have some other fancy integer encoding there, but they are like in very high level, they are similar. And this is shared across multiple symbol tables, so the cost of that is negligible. And if we want to only decode those three elements, then we can easily get into those values without decoding the entire array. And then we go to the values, like basically the dictionary values, and then we can only decode those values without decoding the entire array. So we can have selective decoding, which is pretty cool. And with that, we can do even a step further. How do we evaluate the predicates on encoded data? For example, how do we want to find the string Apache DataFusion? So the conventional approach in Parquet, what we have is we have a compressed array, then we decompress it, and then we decode into arrow format, either in this or in this. Then we run the Apache DataFusion. We will search the array for the Apache DataFusion. But for our case, we want to find Apache DataFusion. What we do is instead of decoding the entire array, we will encode the needle. Okay, Apache DataFusion. Remember, Apache is A and DataFusion is D. So our needle becomes A and D. Then we search the values for AD, which is this part, at index 2. And then we use that index to search the code and return a bit mask of all the values we have. In this case, we can evaluate this string match predicates directly on the compressed data, so we never have to decode anything. And this is an easier case, and a more involved case is how can we find strings that contains DataFusion, basically become a substring match. In that case, most of the system will first try to evaluate the predicates on the encoded value. If it doesn't work, then we have to decode all the way to the original form. And what we do is we can evaluate the predicates on partially encoded data. So this is called cascaded encoding and then cascaded decoding. So we will, in a decoding path, we will experience all three stages of the decoding. And the observation is some of the predicates, for example, like this, finds string that contains DataFusion, doesn't have to be evaluated all the way to the original form. Actually, some of the intermediate stage of the cascaded decoding, we can already evaluate the predicates. For example, here, once we decode the dictionary data, we can easily find the string that contains DataFusion and first decode the value. Then we find the index, find that needle at the index value of 2, and then we return the code, return the bit mask there. So we never have to decode all the way down to the original form. We can evaluate the futures on the just the appropriate stage of the decoding. And that's this partial decoding. And the idea is different filters, they can evaluate at different stage of the cascading decoding, which will save us some of the decoding cost. Okay, and the last technique, yes, the last technique time. Okay, last technique, I call it the random access for latent materialization. So let's say we have two columns, column C1 and C2, and we have two filters. two filters which will apply on C1 and C2. So conventional Parquet ways of doing this is, first we have to decode both C1 and C2, which here we decode 26 rows, and then we apply filter 1 on this column. We get some filter, some of the records match, some doesn't. And it propagated to the second column. Then we apply the filters on the second column, which filter out even more data. And in this case, we have to decode 26 rows. And the later materialization is the idea of we want to decode as late as possible. Okay, so in this case, we first only decode the first row, and then we apply the filter and propagate the bitmax to the second row, which we only decode the matching rows. And then we eventually we only decode 20 rows. So this is late materialization. This is also not new technique, but it doesn't really work well on Parquet because Parquet doesn't remember Parquet have to, if we want to decode this page, this data in Parquet file, you usually have to decode the entire page. So what happens is most of the time, if your selectivity is 50%, then basically every page you have to basically have to decode every page, right? So that is not super beneficial for Parquet, but it is very straightforward for us because we only have to decode the element we want to decode. So decode only the necessary data. And that is our high-level approach. We have multiple compute nodes. We have discrete cache allows you to scale up and down independently. And we have some fancy technique to avoid overwhelming the CPU on the caching server. So those techniques we re-encode Parquet into informal cache-specific file formats, and then we can operate on the encoded values. We have later materializations that can reduce the decoding cost. The last part is evaluations. So this is query 21, and we actually have shown this before. So in our case, we have our system like this, pretty SQL, and we have cache arrow, cache Parquet as our two baselines. Basically, before our system, we have to make trade-off between caching arrow and cache Parquet. And query 21 is look like this. It basically boils down to I want to sum of the columns with some of the filters. Okay, and the filters those are cheap filters, and those are heavy group sorting, computer-heavy operators. And in this figure, we have 3 variants which correspond to those, and on this is the latency, the lower the better, and it's the memory cost, the lower the better. And the caching Parquet is the baseline, which have this, and caching arrow basically similar. Okay, we have better performance, but we have to pay a lot more. In our case, our system is we're better than caching arrow in this case because our memory footprint is much smaller than caching arrow. And our system compress is comparable to Parquet, so it's much better than caching arrow. So we reach the best of both worlds. It is even faster than caching arrow, and we have low memory consumption, which is great. And here's another query which is very similar to query 21. Basically we have some computation intensive work, some scan intensive work. And here's the result. You have basically the opposite pattern, which is you make different trade-off. You pay more, you get a better performance. And what we want to achieve is you pay similar to caching Parquet, then you get a similar performance to caching arrow, which is great. And here's a kind of outlier of the system, so it gives you an idea of when it works, when it doesn't, right? So in this query, this is query 27. it has some pretty heavy computation workload, but the filter is it only have one filter, so URL is not empty. And for that case, almost the entire data set, the URL is not empty. So this is not selecting anything. So if you look at the performance, yeah. So if you look at the query that gets evaluated on the caching server, it basically says this. And the URL is not empty is basically every URL is not empty in this case. Almost every URL is not empty in this case. So in this case, we still get the pretty good compression ratio, even slightly better than Parquet, but our performance is actually not too different from caching Parquet. This is because this filter is not selected, so you have to send a lot of data to the basically says predicate pushdown doesn't really work on the Parquet on the caching server. You have to send a lot of data over the network to a compute node. So we made a separate variant of our system, basically says the caching component sits in the same process as the compute node, which give us much better performance. But yeah, in general, split SQL, our system will leverage the fact that your query has some selective filters, and if you don't, well, yeah, you probably like this system is not really designed for not really designed for that. But hopefully most of the case, unless you are doing batch processing, most of the like real-time queries, you have a lot of filters. And in that case, our system will help you to cut down the network traffic, and yeah, will be cost effective. And this is how we implement the fusion. We basically have goes from SQL to logic plan, and we make into separate plans, and then send the plans to the compute server and the cache server. And so to use our system is also very simple. In fact, in my case, I implement this in our ClickBench benchmark. You only have to change 10 lines of code to benefit from, basically it's a table provider, right? So you just register our table provider and register our optimizer rule, and it's all set. And yeah, having implementing DataFusion means all the systems that implement on top of DataFusion will benefit from it. And yeah, I also want to thank InfluxDB as the sponsor of this work. So without their sponsorship, this will not be possible. And yeah, so conclusion, future work, we make a disaggregated cache so that you can scale independently, you can save a lot of cost, you have stable latency, even if your compute node fails. And it's well suited for queries with filters, which we believe most of the queries has filters. And it's practical. So we try not to repeat the mistakes we have. Like we have low CPU overhead, it's compatible with all the FTP ecosystems, and it works with commodity hardware. You don't have to wait for any vendor-specific hardware to deploy this. And the future work, we want to have some lower network traffic. I think we get some ideas in like the queries we showed before, the high canonical queries, but we can have some advanced technique to cut down that even further. And we also want to have some push down some of the aggregations to the cache server. For example, some of the aggregation are very cheap to evaluate, like a min max. Those queries, they can easily evaluate on the cache server, but we haven't done it now. And we can have even faster decodings, like the caching server, because it's the independent component. It doesn't really interfere with other systems. We can do a lot of fancy things, like you can attach SSD, you can attach HDD, or you can even leverage S3 Express Wandong, right? So we're still working on how do we do the storage aware encoding so that the caching can be even more lightweight. Okay, I think that's the last slide I have. Any questions? Yeah.
What's the thing that you do? Yeah, is it a state of part?
Cache and compute.
Yeah.
It's Aeroflight.
Oh,
Yeah, Aeroflight SQL.
I'm gonna ask my previous question again. As an implementer, like, how close can you get with optimized arrow? Because I think like as an implementer, you'd have to make the choice of like, okay, do I take the concepts of this and go with like arrow that I know can represent all the data? Or like, do I go with a custom file format, but then when I want to add like, I don't know, I want to start using StringView, it turns out that that thing can't encode StringView, and so like I'm completely stuck now. So I'm curious like how optimized arrow can get. I have a couple other questions, so let's start with that.
So actually, what we observe is so we have our own encoding on set of things.
Yep.
Happens in the cache node, and what we observe is it is actually arrow compatible. It's just we represent those data in arrow format. It's just we interpret them differently.
Gotcha.
Yeah. So but if you just want to manipulate the arrow representation, but still have the same semantic arrow, then yeah, having a dictionary encodings, because you only have those set of encodings there, right? So I tried a little bit. For example, when we send the data over network, we try to keep that dictionary encoding. We try to do all sorts of things to be arrow compatible, but the real benefit there for the string compression is really the FSST, which doesn't really do well on.
How does this interact with, like, say, Bloom filters, right? Because like maybe I have a Bloom filter on in my Parquet file that's super selective, and so now it sounds like if I'm going to go with this system, that I can no longer use that Bloom filter.
So I think like the caching happens after the pruning. Right,
Okay.
so you first do the conventional like Parquet or the Parquet pruning
Yep.
step using
Makes sense.
min-max values and Bloom filters, and then you nails down your row group, your Parquet file, and then you try to access the Parquet file from object store. Then you find okay, it's already in the cache.
Okay.
And then the optimization kicking. So you still you still benefit from
Okay. Makes sense. And have you done any work with distributing the cache? Because I imagine, at some scale, at some point, you need to have more than, you can't just have one big computer with cache. You're gonna have to have multiple, and then you kind of get back into all the same problems of like data locality and stuff like that. So like, have you done any work on like, yeah, having multiple cache servers and worrying about data locality and that kind of stuff?
Yeah, that's something like we try not to do because I think it couples the application logic with the infrastructure. So what I hope is, well, people can do different things, but what I hope is we can have compute node attached to one cache server, and if this cache server doesn't really is already saturated, then we provision a new cache server which is responsible for other set of compute nodes. So we kind of partition the compute node and then assign a cache node there. And we try not to say this compute node will connect to multiple cache nodes. That will cause all kinds of communication problems.
Gotcha.
But like, I feel like the work has two pieces. There's like the high level architecture of splitting out the cache from compute, right?
Yep.
And there's a specific implementation that Xiangpeng did of the cache, right? Which is
Yep,
single
yep,
node
yep.
and has specific encoding and stuff for so like, I don't think you have to take all of it necessarily. You can do pieces of it. You can choose something different to put in the cache. You can make that maybe its own distributed service, which is more complicated, but then you can scale the cache capacity and the compute capacity independently. It might or might not be a good trade-off right in your particular system. But yeah, so there's a bunch of different.
Yeah, that's why I'm asking this question. I'm trying to like suss out like, the high level ideas from like, oh, could I implement this? But like, I don't know, I just use arrow or whatever. Because like for us, for example, we have a distributed cache that like has cache locality because like we consistent hash the file names to different cache things. And so like, okay, could we take that and like just switch it from using Parquet to Arrow and get, like 90% of the benefit without like, bringing in new code and re-architecting and whatnot.
Yeah, I think if the use case that dictionary encoding Arrow is already pretty compressed well, then I think that's a very good like a starting point.
I also want to make the point in your slide where you had like 10x compression, that's
Mhm.
like you have like 10 rows. And in
Mhm.
reality, like I feel like a lot of times you actually have like a million rows. And so you're not getting like 10x compression, you're getting like, thousands of x's compression. Because how much compression it gets depends on how much data.
Yeah.
So
Yeah,
the most your compression is actually better than your summon as in real world.
Well,
Yeah,
you're a
could be.
case where there's lots of repeated string values.
Yeah, obviously it depends on the data as well, but potentially
Yeah,
it could be like
yeah,
million
but-
times compression.
yeah, like it depends on the workload. Yeah.
Yeah, yeah.
I had a question about, oh, you guys, okay, cool. I had a question about like, just first off, a contextual question. So basically you're taking already encoded Parquet data and then re-encoding it is, Fastlane then SSST.
Yeah, yeah.
So with that, isn't it like the symbol table and like actually like encoding the data, is that in your experience an expensive operation or what is your experience?
Yeah, that's a very good question. So basically we take some, we have to, like the first time we download packet to our cache server, we have a decode into Arrow, which will pay some cost. And then we transcode into different formats, which is still even more expensive, right? And our hope is we do this once and in background.
Are you doing that? So you're doing that on the,
Yeah, on the cache node.
so would that set it on fire?
Well, like I think what we try to do is this is like a background task that when your system is not super busy, then you gradually make your gradually optimize your like representation, and if this is on fire, then you just spend all the time decoding packet to the normal processing. But if you get a chance to like take a break, then you continuously transcoding that to the better format.
Similar to that, I think is the cache like heat aware at all? Because like for our system, one optimization we did was saying for new data, we don't even compress the Parquet because we know it's going to be like very soon read. And for like caching, we try and keep track of how hot it is and we don't cache it on the first read because we found that like otherwise like you run one query, you fill the whole entire cache, you run another query, you have to evict the whole thing and fill it again. Like how smart is the cache in terms of caching strategies?
Yeah, that's a very good question. So we have caching strategies there, but currently our system like keep everything in memory, and we're working on to tiering the data to the SSD or like S3 Express Quantum, etc. But I think to answer your question, the caching policy, we're not trying to invent fancy things there. We probably just use a very simple LRU or some improved LRU there. And but yeah, we do try to tier in the data to different storage device so that we can be more cost effective. Yeah, because everything staying in memory is not not always great.
Okay, so one question was answered about the kind of amplification of writing to the cache, but the other one I had was, so you mentioned like the other file formats that have started to come up like Lance and Nimble.
Mhm.
If the problem or the trade-off with those is you know if you have an open system, you can't have other tools necessarily like adopting them or interacting with them. But could you put something like Lance, which supports like fast lanes and FSST, kind of in the cache layer? Like, if I was someone who was like going to implement something like this. And then my next kind of follow-up question is also like if I'm like a closed system, do you see like benefit in like pushing the file format, whether it's the custom kind of encodings you're doing or something like Lance or Nimble, like all the way down to the object store, and basically not using Parquet?
I see. I think to answer your first question is okay. Yeah, I think like we actually start with Vertex on the cache server, and I think we do think we will eventually use Vertex again, but like for currently for very rapid prototype, we are not using Vertex now, because we really want to have those nice features like evaluating on the partially encoded data. So we really want to be control of how the decoding pipeline works and how we can like operating on those like specific data there. So yeah, eventually I think it's like a system like the other file format, they may have support for those set of features, but if they do, we will probably switch to that. But I think one of the advantage of our approach is we were not using a written like a specification of the file format. So it means we can do a lot of query specific optimization there. Well, although we haven't do it, but it's opportunity there, yeah. Because everything happens in the cache node, stays in cache node. We don't have to like say to promise anything to the rest of the world. Yeah. And the second question, can you repeat the second?
Like if I was a closed system where I had some of those features in the file format itself, do you think a cache layer that just caches like the content of the file would be like somewhat as effective as this?
I think first of all, having those nice features, like most of the gain actually comes from partially decoding or late materialization, or all of these things. You really have to work with the query engine to make it fast, to leverage those features, right? So if you have a customized format, it starts well with on S3, and then you have to modify DataFusion so that DataFusion can understand your format and leverage all those kind of things, which is non-trivial amount of work. Like DataFusion have very advanced support for Parquet, so that's why we start with.
Should be my last questions because I know we're over time. I have like a low level question and a high level question. Low level question is like the splitting of the SQL, and you showed it kind of happens at the, I think it was logical plan level and stuff. Like, how much of that are you doing something custom versus it's like what DataFusion does? Because I feel like DataFusion already kind of does that in the sense that if you're a table provider, it it takes a SQL and it distills it down to like the tables that need to be scanned, and it gives you the filters that it thinks can be pushed down into that table.
Yeah.
So are you just a table provider that takes those filters, or are you like doing more in-depth manipulation of the SQL?
Yeah, that's a very great question. Actually, our current implementation just behave like a table provider and take the filters there. But we also observe that some of the aggregates that are not pushed down to the table provider. But we want to cache server to evaluate those aggregates. So yeah, we are switching to this. Yeah.
That makes sense. Yeah, I think that's an interesting question because again, like from an implementer's perspective, it's like, can I just like make this a part of my table provider, or use a different exec implementation instead of Parquet exec, I use your thing, in which case like maybe it's easy and that gets me like 90% of the gains.
Yes. Yeah.
Versus like there's a 10% of gains, which I'm sure is like really great to publish a paper on, but if I'm an implementer, it's like maybe like, yeah, I don't really want to rewrite my entire code base, so I'm not going to adopt it. And my high level question is like, yeah, how much of this are you intending to be like, like an implementation that's out there that I can like as an implementer go and say like, hey, I'm gonna pull in this crate, I'm gonna edit a little bit of my code base, and now I'm using it, versus like, it's more conceptual, like because there's stuff like, yeah, with the file format, do I start using it and then I get errors because it doesn't support like some column type or whatever.
Yeah.
Which is like, okay, yeah, if I'm publishing a paper, I'm using ClickBench as my metric. ClickBench doesn't have a, I don't know, geo column.
Joins, for example.
Yeah, sure, it doesn't have to, so it doesn't implement that, which is like, makes total sense, but then if I'm gonna put it in my system, I don't want to like spend hours implementing it and then find out that like I can't use it off the shelf thing. So how much is it off the shelf versus like, research oriented?
Yeah, I think the goal is I want to make it off the shelf. I want to make a DataFusion cache crate which you can download and then modify 10 lines of code, then you can use it. Okay. But yeah, as you mentioned, there are a lot of real world cases where people do a lot of crazy things. And our approach is we will have a caching server which will optimistically, so if we identify string arrays, then we do string arrays for that. If there are some certain type we don't know how to interpret, then we just keep there and we don't like change the format there, so we just send to the computer server, which you don't get the benefit, but it's still not breaking your system. Yes, like the high level goal is, yeah, I try to make it off the shelf and make it like a system that every system can use. Yeah, basically, that's my goal. Yeah, and also publishing paper, of course. I have to graduate. Yeah. Okay.
Thank you. Awesome.
So can take it offline.
Did you want to ask a question? Or should I- Okay, so I think we have lunch now. We should have lunch. And then we'll stay around maybe at 1 o'clock. We'll the last presentation.